So we are being recorded now. So here we go. So we have John Cassetta with cubes. So John, are you ready to present?
Yeah, I'm ready.
Okay. Yep, I can see your presentation. Yep.
I'm not sure exactly how this works. Are you seeing it change here?
No, I'm just seeing the Devo page.
Okay,
Are
right.
you changing it?
I'm trying to see. Okay.
So what I see is slide 1 of 11. So it's probably your presentation screen that we're seeing, I'm thinking.
Oh, okay, I see how it
Yeah.
works. All right.
Yeah, it's advancing now. Okay,
so the verse I had was from Romans 11:33, and it says, "Oh, the depth of the riches and wisdom and knowledge of God! How unsearchable are His judgments, and how inscrutable are His ways." And like, it's a pretty simple verse, but I think it's really encouraging because basically God doesn't make any mistakes, So even things that seem bad to us, like the coronavirus situation and things like that, are still like part of His plan. They're going to work out, But yeah, so anyway,
yeah, certainly beyond our comprehension for sure. There's lots of things like that where I know when I get to heaven, it's like, oh, I didn't quite get this, but now I get it.
Yeah, because it seems like there's no way that having something like this could be good, but that God did it first for some reason, even though we don't know what it is. And so, okay, oops. I'm going to be printing on Cubes OS, which is a security-based operating system. And so it just is intended to make the user, protect the user really well. But I think it does it in a really interesting way. So that's what I'm going to be talking about here. So Cubes OS.
Did we lose John?
Yeah, I think he was kicked out for a minute.
Okay.
Yeah, I'm not sure what happened there.
Yeah. I'm
okay,
like,
that's
interesting.
Yeah. Haven't seen that before.
Okay.
Yeah.
Anyway, I guess we'll just continue. So, it's basically was created to provide protection for vulnerable individuals, such as like journalists, political activists, whistleblowers, and researchers, like I said here. And it uses a security by isolation approach to provide the security. And the way that works is it uses the Zen hypervisor to create virtual machines that are called cubes or domains based off different operating systems. And the hypervisor definition from the textbook is basically it's the same thing as a virtual machine manager. It just provides an interface for you to create and run virtual machines. So basically, each domain you can do different things in each domain, and so your data is spread between them. And the point is that if malicious software got access to one of the virtual machines, it can't access any of the other ones. So each domain has like a few sort of like attributes. Each one you have for a specific purpose, and that's like all that one will do. And you have a nature, which is what operating system it's based off of. So they can be like, they have a pretty significant amount of them. There's a few listed there of operating systems you can use, and they each have a colored border, which you can't change, that indicates how secure that domain is. So the administrative domain is like the one that opens when you turn on the operating system, and it controls your I/O devices, and it displays a desktop so that you can create other domains from it. And it has absolute minimum of contact with the other domains that you create. And so there's also application virtual machines, which are basically a virtual machine that you open and it only runs one application. And so you can put them in a security domain or just on a disposable virtual machine, and it'll be destroyed when you close it if you use that. So like here's a thing about, here's like the colored borders you can see. Like the green one is the safest, so it has like the work on it, and then for like personal use you can use a less secure one because it doesn't matter that much. But you just have them all separate. So here's a graphic from their website about how it works. The important thing is like the color code at the bottom that says how safe it is. So like the disposable app virtual machines are probably not very safe, but it doesn't really matter for those because you're just using it once essentially. And then for things like your work and like the GUI domain, the administrative domain, are all really safe. So some of the benefits of it basically are just it's a lot of security from being hacked or like malicious software. And what's also kind of nice is you can use a lot of different operating systems if you want. So like if you're taking this class and you need to use Linux or something, you can just create a virtual machine for it whenever you need to. And also it gives you protection against like making mistakes yourself, because basically no matter what you do in a virtual machine, it's not a big deal. You just close it and make a new one. And so there's the references. Are there any questions?
So have you, John, have you actually played with this yourself, or did you download it and try it, or not?
I have not. I've heard that it's not super easy to use.
And certainly you would imagine the performance is not that good. Everything is in separate virtual machines, which keeps it isolated. But doing much would be a lot of effort, I would imagine.
Yeah, it's definitely safe, but you probably don't want to use it unless you have to.
So are there any other questions for John? All right. Well, thank you. Great job.
Yeah, thank you.
Okay, so I think the last one is Tim with the Android operating system, and I think he's looking at the oxygen release is the version he's going to be looking at. But his is the next and I believe last presentation. Administrative items. We're getting down to the end here. We have a quiz on chapter 9. And that's due tonight. And then Monday is the mass storage programming problem. Again, you're simulating the behaviors of the cylinder travel on the machine, do some type of output statement to the screen as you traverse the different cylinders. And then there's then a question about how many cylinders were actually traveled for each of the different algorithms. Yeah, you just queue up the requests in your data structure of choice, and then go through them and check out the different algorithms and see how they behave. And then there's the extra credit programming assignment, which is chapter 12. That's 10 extra credit points. And then Friday, or that should be Tuesday. I still didn't correct it. I should have corrected it. That's Tuesday, May 5th, not Friday. Is the remaining of the quizzes due? That's the day before the final is due. The final is due on May 5th. And then I did announce last time that if you either have no zeros for any non-optional programming projects, or if you are a senior on the exempt list, which is basically you qualified to skip the final, I'm also allowing it. And so not taking the final will not have an impact on your grade. So that is an option you can take. But then, of course, you could take the final in an effort to improve your grade. If you want to try to pull up your grade with all the points that are available for the final, you can choose that option as well. So those are your choices. You can either decide to stay pat with what you have, that you're happy with your current grade, or you can try to upgrade your Sorry about that. I muted myself. So any questions about those items? Okay. Sounds good. So going back to chapter 12, which is file system implementation. So we were moving on to file allocation table, or FAT, which it was used in DOS. But we started where we got to from there, what was the linked allocation method, where all the data is located on the disk, and included with that is the information to where the next block for a particular file is located. We talked about how reliability can be a problem, because if the link gets corrupted, you may lose the rest of the file, lose access or linkage to those blocks. And then the other issue is they will be marked as used, but not be able to be recovered. So, and then the efficiency, the storage efficiency in having a pointer associated with every block of data also can be a problem. So the FAT system is a variant of a linked allocation scheme. The beginning of the volume has a table indexed by blocks numbers, as it says there. It's like a linked list, but it's faster on disk and cacheable. So the scheme here is that you have this file direct. So this is your file information, the metadata, the inode, or the just went blank on the other term, but you know, you get the point. It's the information pointing to the file that represents a file, and you actually have the pointer to the location, and it's a linked list, but it's stored in a variant method that improves on the efficiency by organizing it in this way here. That's depicted in the diagram. So you can see here that it points to 217, and then this one then points to 618, and then 618 points to 339. And here is the linked list, but it's stored locally as the allocation table. So it's not actually associated with each of the data elements and then its next block, but it's actually allocated in a table like is shown here. So this is the variant used for FAT. We still, as old as it is, we still see FAT, especially on USB sticks, you'll see it. But then as the size of USB sticks have grown, other methods have had to be used when it exceeds what can be handled by the FAT system. In particular, we use, the latest I believe is FAT32. So here's another method, which is a indexed table. So here we have the index here pointing to the data. And then here's a pictorial diagram below it of how everything would map into the hard drive. You have this table here that then points to each of the different blocks, much like the FAT system. So you need the index table, but one of the so each file has its own index block, so you don't have a global one necessarily, but each file has its own index of pointers to its data. And so you can see here, here's 19, which is the set of pointers to information for that file. And you can see that we have references to 9, 16, 1, etc. And then the -1s would reference the fact that there are no blocks that you've reached the end of the file. So that gives you a nice random access method to access the file, and allows you to quickly map from the logical file space to the physical information on disk. Again, there's remember that each file has its own index blocks to its data, so that it's on a per file basis. As we get to larger files, other schemes are used. Here we have a block of the index table. So here we're dereferencing it, and displacement into the block of the index table. So again, we've got another level of abstraction, and this is done primarily to reduce the size of the search time and the size of the index table by breaking it up into portions. And you can imagine you could also go from a single level to a 2-level index, which is depicted here. So a 4K block could store 1024 4-byte pointers. And again, you could, by adding the extra layer and level and direction, you cause another reference to be used in order to get to it, so it slows performance, but the actual storage needed to store the data can be reduced. And then we have the Unix UFS, or Unified File System, which is a mechanism for abstracting away to a central method, which is very tightly tied to the Unix way of organizing files, but it allows a common interface to multiple different file systems so that you can have the same interface used by various layers that would then map down to other file systems so that you have a universal layer. So there are various things to consider when you're thinking about performance of particular ways of storing information on disks. Performance is just one of the metrics. The other one is how does it handle failures, and how robust is it in handling it, and how good is it for preventing possible losses of data. But performance depends on the access type. So again, we talked about contiguous is great for sequential and random access, but it does have the downside of fragmentation. Index is more complex, but again, the index reduces the fragmentation, and you then have the extra performance hits on having to go to do multiple references to actually get to the data you want. It's dereferenced, so that will degrade the performance. But then we also talked about clustering as a way to then increase the performance, that you can cluster groups of blocks together and treat it as a single, basically treat it similarly to a larger block. And so it's by grouping them, you try to get the best of both, where you have a mechanism in the blocks, the smaller block sizes, to reduce fragmentation, but you have the efficiency that if you can put blocks together, that you can handle as a single larger block. Free space management is the other part of this. Is not only do we have to be able to figure out where blocks of data are for a file, but we also need a way for the system to determine where the free blocks of data are located. In general, it is not feasible to keep the entire list of free space mapping for a large disk in memory. So again, we typically will have to have some type of buffering onto the hard disk involved with the free space list. And so the simple scheme that is very commonly used is a bit vector or bit map, basically mapping to the free blocks. So in this example, we have bit 0 up through n-1, and if the bit is set to 1, that means that space is free, and if the bit is set to 0, it means that it's occupied, that it's being used. So for instance, if we had a 1 here in the 0th position, then we know that that was free. And so let's say we had 1 0 0 1. So if this third block was set to 1, we know that was free, but the 1 and 2 blocks are being occupied. So that's a nice, easy way to do it, and it has great advantages in that the bit map, the byte array, can be manipulated using masks, which is basically logical bit operations to gather information about what you're trying to gather. So there is some efficiency in terms of hardware in algorithms that use this scheme, and so that's why this is a very popular scheme to do it, is that it maps well to the hardware operations that are available to you. Basically, the CPU instructions can be very good at helping you manipulate, doing these bit manipulations. So another way you could do it is a linked list. Sounds pretty straightforward. I'm sure you understand this from your data structures class. You could just have a list of free blocks, and my cursor's caught on the other screen. Here we go. And just basically have a pointer to the free disk, which would then have a pointer to the next free element in the list. So a linked list. You can do efficiencies in terms of grouping them. Again, that you could say that all these are continuous and then are tied together to avoid the number of pointers that you use. And then there's various counting schemes that can again be used in the process of having continuous allocations when they're available. Extents and clusterings or other aspects in it. So these can all be mapped in to a linked list scheme. They're basically all variants off of a linked list that you can do to manage the free space pool. And that's grouping and counting is the names of techniques. But again, I'm not gonna I'm not gonna basically hold you to these, but just keep in mind that there are multiple schemes based on the linked free list that are used in managing your free space for on a hard disk algorithms. ZFS uses the concept of a metaslab, and metaslabs are just, again, this idea of having various block sizes that you can use to reduce the fragmentation, but then you consolidate them or condense them into larger blocks when they are contiguous. And ZFS from Solaris uses a system called ZFS, which calls them metaslabs. And it also takes advantage of a balanced tree structure in order to manage the free space. Other efficiency and performance things that can be done is keeping the data and metadata close together so that when you're reading the data, the metadata is going to follow next. You need to have the read of the data and the metadata at the same time. So why not co-locate them close together? There can be buffering in main memory or other types of memory. For instance, that there could be caching available on the hard drive itself. So basically caching. And then also having specific commands that your hard disk can handle, either synchronous or asynchronous writes, is another efficiency performance thing that can be done. And not mentioned here, but we talked about direct memory access, DMA, which is direct access by the disk of memory to take the CPU out that can improve the performance of the CPU by allowing unused cycles to handle the disk I/O process. And then there's other techniques called free behind and read ahead techniques, which is basically methods of looking forward based on history or looking ahead to optimize your performance in terms of handling disk access. Reads are frequently slower than writes in some case, which is interesting that it's opposite of what we have in the solid state drives, where typically the reads are faster than the writes. But with hard disk, with magnetic media, it often turns out that the reads will be slower than the writes. So certainly performance is one issue, but as I talked about, you want the reliability of the data to be good as well. And we know that magnetic media does have issues with eventually the bytes not working, or having to map areas of the disk that from the time of manufacturing are bad sectors and bad portions of the disk that can't be used. So because of this chance of failures of data, we need to come up with and use schemes to prevent loss of data. So consistency checking is one, which is you constantly compare data and look for inconsistency, but it can be slow and sometimes fails. We can have error correcting data appended or metadata appended to your data that gives you indication that it's failed. Certainly backups are important. You're all familiar with the concept of constantly backing up your data to either another hard drive or tapes. Is the long-term archival solution is magnetic tapes that we talked about, and then restoring the data from a backup if corruption is detected. Another technique comes from the database world, where you log or journal all the reads and writes to the system and treat it as a transaction. And if you detect a failure, the hope is that you can recover by rolling back operations from the journal or the log. So you'll see this in just about all operating systems. I've actually played around with the journaling a little bit in Linux, making sure that recoveries of database or critical information can be restored. And so I think I've covered just about everything here. Transactions are large asynchronously, but they're written to a log. File system crashes. All remaining transaction log must still be performed before it's considered consistent. And the chances of you can actually recover from a crash from your log structure, but there's also of course, the issues where you have to be able to protect the logging structure itself, or be able to look for inconsistencies in the logging structure itself. So the other thing is network file systems. So operating across a network and accessing files across a network in a LAN or a local area network or a wide area network, LAN or WANs. It's part of the Solaris and Sun operating systems. I think a lot of you are familiar with Sun's mantra and advertising slogan, which was the network is the computer, which was pushing the use of interconnected workstations as a network of independent machines to give a overall synergy and as a replacement for large mainframes, a bunch of different independent machines all connected through a network. And so critical to this was their network file system, which allowed you to access remote files as if it was local, but being over the network. It was designed to operate in a heterogeneous environment of different machines and different operating systems and network architectures. So it was, again, targeted not only with Sun workstations, but targeted at a heterogeneous environment of multiple different operating systems and network architectures. This slide just basically repeats what I said here about the heterogeneous environment. There's some implementation details and usage behavior, but NFS is a large staple in operating system. It was very successful in when it's done, and there have been lots of systems built off of NFS as the key component, and I'm sure you've probably run across NFS file systems. So there are three major layers of the NFS architecture. Again, it's an abstraction that is an abstraction layer that removes the differences between the heterogeneous systems so that they can be treated the same across different file systems and different operating systems and different network systems, and using a standard NFS protocol. It allows for heterogeneous systems to be treated in a homogeneous manner in terms of access to files remotely over the network. So one system that actually uses NFS or CIFS or other protocols underneath it is the Waffle file system, and that's used by network appliance systems or NAS. It's a very powerful way of sharing multiple disk farms and machines together to form a single file system. Again, I mentioned it. It serves up NFS, CIFS. CIFS is another term for Samba. If you're in the Linux world, you will hear the term Samba. And heavily used in the Windows environment. And it's has sort of lots of similarities to the Berkeley fast file system. Not that I would expect you to know it, but one of the key features in Waffle is this concept of a snapshot, which makes it very powerful. So here you can see here in step A, it's before a snapshot. You have your root inode with all your different blocks of data, and then a snapshot is taken, and it actually then has references a snapshot to all the data that existed at a particular time. So the advantage of that is basically in the network file system that I use, the NAS system, we actually could count on an hourly snapshot of all our data. And so that if you needed to go back and recover an accidentally deleted file or data that you suspect has been corrupted, you can go back to the snapshot and recover it. It's designed in such a way that it's an extremely efficient mechanism for capturing these snapshots, and that is basically the calling card of NetApp and the NAS file systems, which are heavily used in industry for all these big business data applications and things like that. And then when I was working in the government, we used that as well for various applications. So it is a high reliability environment where data can easily be recovered if it is accidentally deleted, lost, or corrupted. That there is a lot of redundancy and recovery options built into the Waffle system that's used by NetApp. So that concludes the file system implementation section. Anyone have any questions on any of that? Okay. So moving on, we are now going to look at I/O systems. So one of the primary uses of I/O systems we saw was in accessing of hard drives, magnetic media, or solid state, that you do need to have I/O. But other places where you would do I/O are like keyboards, mouse, right? So input-output devices for the user interface that the user interacts with. These are all different forms of I/O and something that is provided by your operating systems in order to allow you to do these things. So the first bullet is pretty much things that I just informally went over already. And then we have ports, which are I/O ports. You can think of as like serial ports and things like that. We have buses. So USB is an example of a bus, and SCSI for hard drives is an old standard bus for accessing disk, which have kind of been superseded by other schemes for performance and or cost reasons for cheaper schemes. But and then we have device drivers, which is software that encapsulates and abstracts the details of the use of the device. So again, remember that device driver is software that encapsulates device details that present a uniform device access interface to the I/O subsystem. So it abstracts it into a common model. And so therefore, application code or even system code at higher levels don't have to know the details of how the hardware device works. They just deal with a higher abstraction that is provided by the device driver software that provides that abstraction. So we have various forms of I/O hardware. You can look at the diagram there, and you can see the SCSI bus that I talked about for accessing SCSI drives. We have the PCI bus, various expansion bus, all kinds of different buses that are available, FireWire, all kinds of different things have been proposed and used. Some characteristics that you have are daisy chain in a bus where one device communicates to the next device, which then passes it on to the next. That's a daisy chaining way of actually creating a bus. And expansion buses, which are used for relatively slow devices. Let's see, here we are. So here's your expansion bus right down here on the bottom. And so here we have keyboards, serial ports, which are in today's standards, slow communication mechanisms, parallel ports, things like that would be part of an expansion bus. And then we have controller or host adapters, which is basically hardware that interfaces a device to the bus. or some other part of the system. They're often integrated into the device, the I/O device that we're looking for. But sometimes it can also be a separate circuit board or host adapter that's involved. A lot of times they'll contain their own processor and microcode and memory, so it is essentially its own little computer that services this I/O. One place that I'm sure a lot of you are familiar is, especially you gaming majors, is GPUs, which are graphical processing units, which are, in a sense, their own computer in their own right. And that's for manipulating I/O for the purposes of displaying information on screens. So there's a case of definitely a very powerful computer. In fact, GPUs have been used because of the sophisticated computer that graphic boards are. GPUs are actually often used for various signal processing applications or other applications that take advantage of the power of a GPU for things other than doing graphics. So those you can see. Again, the devices are typically connected using either ports, a bus, or a controller, i.e. a host adapter. So those are the most common methods of connecting a device and providing input-output into and out of those devices. So there's I/O instructions that actually control the devices. Typical ways you can do it is registers in the device itself will generally have its own registers, and you'll have a data in register and a data out register. Status register, which provides status of whether information has been transferred successfully or not. And then control registers are actually initiating a particular operation. So register usage is one common way of controlling the hardware is through specific registers in the device. And as it says here, they're typically 1 to 4 bytes, and or a FIFO buffer is another mechanism that can be used. Another popular way is a memory mapped device here. So there you actually address the data and the command registers as if you're just writing to memory. It's mapped into the memory space of the computer. So of the CPU would just treat it as if it's a memory, but it actually gets mapped to this I/O device. So when you're writing into these particular areas of memory, you are in fact writing to the device. And again, the example of graphics is a very common use for a memory mapped scheme, because we're talking about large address spaces when we deal with graphics. So here's just a diagram depicting I/O address ranges and devices on a PC. So this is not an exhaustive list, but these are standard locations, I/O address locations for various types of drives. You can see here, this one right here is starting to go away. I think you're be hard pressed to see too many diskette drive things, but there are certainly legacy applications out there. In fact, my company had some legacy machines that they're still supporting, or at least were still supporting when I left the company, where they actually did have to figure out how to get disks to our customers because they have these legacy machines that we were still supporting. So techniques for, let's see, go back. Yeah, all right. So techniques for actually accessing these devices and controlling them. One way is polling, where for each byte of data, you're constantly reading the status bit to see what the status is, and then reading or writing data, and then setting a command bit, and then constantly checking the status bit to see if the operation succeeded, and that you can go on and do the next operation. You can see here the controller sets a busy bit and executes the transfer, and then clears the busy bit when the thing has actually been completed, and can set an error bit or command ready bit when it's ready to transfer. So one of the things that is characteristics of a polling scheme is that this is usually reserved for very slow transmission devices that don't have a lot of data. So one couple of cases you can think of is keyboard and mouse input are cases where it's in computer terms, it's relatively small amounts of data going across fairly slowly. One thing is that you want to make sure that your polling cycle doesn't affect other devices again, so you would poll on an infrequent basis. And the other thing is it's a reasonable approach to take if the device is relatively fast compared to your polling time, but inefficient if the device is slow because you're constantly checking the device, looking for the next status, and you don't want to be checking lots and lots of times compared to when the status actually changes. One of the other characteristics of this is if you actually are polling and miss a cycle, you can end up with overwritten or lost data. So that's something to keep in mind with polling. So of course, the next method is interrupts, which we have discussed in lots of different areas of this class. So polling can happen in 3 instruction cycles, but CPU interrupt line is triggered by the other device and is actually done in the microcode for the processor. So it happens quite quickly, and therefore is a much more efficient way. You don't have a process that is periodically polling an area. It's happened by the interrupt control lines, which is the microcode handling that, or the CPU itself, the CPU electronics itself that's handling these interrupt lines. And we talked about mask, that you can actually enable or disable various interrupts, either temporarily or permanently through masking off particular interrupts that you want to ignore. This can be done in the middle of interrupt. It's typically done in the middle of an interrupt code that's handling something that will disable other interrupts while it's in the middle of doing its operations. And then we talked about earlier the interrupt vector, which dispatch is the address, which it's a vector of addresses that go to the individual interrupt handling routines for those interrupts. So again, it's a vector of all of the interrupts that can possibly be triggered, and then the address to that interrupt service routine that's handling that interrupt. Interrupts can be priority based. You can give various priorities to particular interrupts versus other interrupts that certain interrupts will be handled more with a higher priority or will be put to the front of the list. And then we have some that are non-maskable, which means that there is no way to prevent that particular interrupt from happening. It's an important enough task that we don't want it to be able to you want that interrupt to ever be ignored. And then we also have the concept of interrupt changing, which is where more than one device is tied to the same interrupt. And then once the interrupt happens, the interrupt handling code then has to determine through chaining what device actually triggered that particular interrupt. So key things to remember here is that they are maskable. You can disable them, and that interrupt handling is dispatched by the CPU checking the interrupt request lines after each instruction and checking the interrupt vector to dispatch to the correct handler based on the addresses in the interrupt vector. Here's just a diagram depicting a typical interrupt-driven I/O cycle. I think we've seen this before. You can take a look at it. Let me know if you have any questions, but it's pretty straightforward and pretty understandable that we initiate the I/O and then interrupts happen back and forth. And this is basically a flow chart depicting the operations between the CPU and the I/O controller here. So here for the Intel Pentium processor is the interrupt event vector table. So here's the vector number for each of these different things and the description of the interrupt handling. So here's division divide error, basically division by 0, stack faults, general protection, maskable interrupts down here are 33 through 255, just sort of representation of what a vector table for the Pentium looks like. Interrupt mechanisms are also used for exceptions.
Professor Lim?
Yes.
It's 253.
Okay. Yes. Well, thank you for that heads up. So any questions before we call it quits? All right, we'll go ahead and stop recording, and thank you for